Hi, Year 11, so we're going to look at your paper 6. You can see it was the 2021 paper from November, so it's a very recent paper. So question 1 is about thermal physics. So you've got a student investigating the effect of insulation on the cooling of water. Shoes of the apparatus shown in figure 1.1. The sides of beaker A are covered with material that is a thermal insulator, whereas beaker B has no covering. And you can see a thermometer and then a zoom in of the thermometer reading, and it says please record the room temperature theta R shown on the thermometer in figure 1.1. Okay, so you just look to where the thermometer level reaches, and clearly that is 21 degrees Celsius for 1 mark there. So then it says the student pours 150 centimetres cubed of hot water into beaker A and records the temperature at time t is 0, and then the temperature of the water is recorded every 30 seconds, and then repeats the process for beaker B. Add units to the column headings in table 1.1. Really well done. After I mentioned this to you before your mock, you all got these marks, which is pleasing because normally I always spot someone that forgets. So units for time are seconds. These are temperatures, so it's degrees Celsius, gets you 1 mark. So then it says in C, describe 2 precautions that can be taken to ensure that temperature readings are as accurate as possible. So the number that you say it really is. So first thing is viewing the temperature scale at eye level and reading perpendicularly. So read the scale at eye level and perpendicularly. Okay, so that's 1 mark. And then the second thing that you can do is to wait until the temperature stops rising at the start. And there is a third option here as well. You can avoid the thermometer from touching the glass beaker. So I'll add a 3, but obviously you only need to write 2 of them. Okay, so you don't want the thermometer to touch the glass beaker. So write a conclusion stating whether the insulation affects the rate of cooling of water. So you're talking about the insulation and the rate of cooling of water. Remember that rate is how quickly it happens. Okay, so whether it cools quickly or slowly. And then most importantly, it says justify your answer by referencing the values. So if you didn't have any numbers in your answer, you didn't finish the question. Okay, because it tells you to reference values. So, because we're looking at the rate of cooling, we're going to want to look at how much cooling happened in a set amount of time. We cannot just look at the number at the bottom and compare them and say, well, this is lower than this one, so this one cooled more, because they didn't start at the same temperature. So we can't just compare final answers, because we're not comparing a similar situation. So what we have to do is look at how the temperature changed from the start to the finish. So this is obviously over 180 seconds. This one obviously went up by, can't count today, 6.5 degrees Celsius. And then this one here changed significantly more, and it went up by 9.5. Okay, and so let's have a look. Write a conclusion stating whether the insulation affects the rate of cooling. So with insulation, there was less cooling across the same amount of time, whereas without the insulation there was more cooling over the same amount of time. So what we want to say is insulation, because that's what we're talking about, how insulation affects this. So we're going to put in a word here that links the insulation to the rate of cooling. So we're going to say insulation decreases the rate of cooling. That's our conclusion, so that's 1 mark. Okay, we see this because in 180 seconds, that's one of my results, beaker A had a temperature change of 6.5 degrees Celsius, which was less than the temperature change of beaker B, which cooled by 9.5 degrees Celsius. Okay, so I reference the difference in the change in temperature and the time, because it doesn't ask how it affects the total cooling, it asks how quickly it happened. So I have to refer to the time as well in my answer. So that was D. Then it says in E, to calculate the average cooling rate X1 during the first half of the experiment for beaker B. Use the readings for beaker B from the table and the equation temperature at time is 0, temperature at time is 90, and T you're told is 90 seconds. So X1 is going to be equal to theta naught for beaker B. If we go back to the table, the temperature at naught for time for beaker B was 87.5. And the temperature at 90 seconds was 80. And the time that happened over was 90 seconds. So we're going to have a difference of 7.5 over 90, and that gets our cooling rate. Sorry for the noise, just pulling my calculator out. And that gets us a cooling rate of 0.08. Now, the top of the fraction is a change in temperature, so that's degrees Celsius, but we have to divide that by the bottom, which was a time, which is seconds. So where it says include the unit, I have to do that, and it's going to be degrees Celsius per second. For X2 we do it again, it's still for beaker B, but this time it's for 90 and 180. So we saw that the temperature for 90 was 80, this is for X2, and now we have to find the value of the temperature at 180 seconds, and that was 78. Okay, so this time, the time is still 90 seconds because it's between 90 and 180. So I've got 2 over 90, and I'm getting 0.02 recurring. But again, it's degrees Celsius per second. Okay, you get 1 mark for the correct calculations for both of these, and you get 1 mark for them seeing the unit at least once. Okay, then it says in FI, suggest an additional experiment to test whether the lid affects the cooling rate of water in beaker B. So if we go back to the original diagram, you can see that we did have a lid for both of them. Okay, so all we need to do for beaker B to test to see whether the lid had any effect was to repeat experiment for beaker B, but this time without a lid on there. Okay, so we set up an identical beaker to B, but remove the lid and calculate the rate of cooling for it. Okay. Then in FII it says a student suggests that the temperature of the water in beaker B at time is 0 must be the same as in B for the comparison to be fair. Suggest whether your results support this suggestion. So we need to have a little look at this quite carefully. So I've come back to my table. So this was part B, which the question that I'm currently doing refers to. And remember that what we've just said is that we want to look at how the lid affected the rate of cooling with beaker B. So this one had a lid. And what we've just suggested is that we test beaker B without a lid. And we check the rate of cooling. So we look at the temperature and we collect results. Now, what the question is asking, if I look at it carefully, is should I make sure that my temperature at time is 0 here need to be identical to this? So the question is, does this need to be 87.5 degrees Celsius or not? Is that important to make sure that the comparison is fair? Well, the answer is yes. Okay, it does need to be the same. So the first mark comes from saying yes, it's true. Okay, it is necessary. We've seen in E, which is this bit, that when we started at different temperatures for A and B, we ended up with different rates of cooling. Okay, we clearly have different rates. Now we could assume that that's because of the difference, because one has insulation and one doesn't, but we now can't be 100% sure that that was the reason why. It could also be because we didn't start from the same temperature. So we're not absolutely sure that that is what we tested here. We're not completely 100% happy that our conclusion is due to the insulation and not due to the difference in the start temperature. So in order for us to be able to say with certainty whether the lid affects the rate of cooling or not, everything else must be controlled. Okay, so we saw different cooling rates for A and B, and we can say the numbers: 0.08 degrees Celsius per second and 0.02 degrees Celsius per second for start temperatures that were different. And they were, if we go back to our results, 88 and 87.5. Okay, so we don't know whether or not starting from a different temperature is why we've got different cooling rates. Okay, so we therefore need to make sure that we have identical start temperatures. Okay. Number 2 then. A student compares the resistance of 2 wires. Chooses a circuit which is shown. On figure 2.1, complete the circuit diagram to show a voltmeter connected to measure the potential difference from X to Y. Okay, so let's do that bit first. So I'll get my pencil. So remember, with our voltmeter, we put it in the circuit at the end. It has to be in parallel. So if we imagine what a voltmeter is doing, it has 2 wires that we connect to. It will measure the potential at a point here. It will measure a potential at a point here, and the value that you see on the screen is the difference in the 2 values. So if we want the potential difference between X and Y, we want one of the wires to be connected to X, and we want one of the wires to be connected to Y, because that will be measuring the potential at X and Y. And then the voltmeter will tell you the difference between the 2. Okay, so we just needed to simply connect those there. Then it says add an ammeter to connect and an ammeter connected to measure the current. So we now need to make sure that we've added an ammeter. Okay. Now, we also should notice that the power supply has not been connected up yet, so we need to finish that off and make sure we do that. So what we can do is add our ammeter in. So this is our power supply. The current's going to come out and through the ammeter and measure the current via the ammeter here. It's going to be connected in series if it's an ammeter. We then have X connected through the resistance wire A or B, which connects back up to Y, but we need to complete the circuit, okay, because there has to be a complete loop around the circuit, so we can't have gaps. Okay, so that was the first 2 marks for putting the voltmeter and the ammeter in the right place and making sure we've got a complete circuit. In B, it says read and record in table 2.1 the values of V and I shown. Now this was done surprisingly badly by a number of people. It's just reading the scales, so we need to do a little bit of practice. So look carefully. If we've got 2 here and 3 here, halfway between is 2.5. Between 2.5 and 3, we've got 5 dashes, so each little dash is worth 0.1. So this is clearly 2.3 volts on this one. Okay, I've got 0.2, I've got 0.4. Halfway would be 0.3. There's 5 dashes between 0.3 and 0.4, so each dash is worth 0.02. So this is 0.32 amps, and people were just not looking very carefully at this, and it led to quite a few mistakes. So please be careful. You're then going to put that into the table. I've just realised I've made my own mistake. This is not 2.3. Oh my goodness me. It's 2.5 plus 0.3. This is 2.8. Yikes, I've done exactly what I've just said that you all did. My bad. But it is important that you double check your answers at the end of your paper for this exact reason. So 2.8 and 0.32. So then we just pop that into the table. So we had 2.8, 0.32. Okay. And then once I've got that, we've got some things to calculate. The student connects the crocodile clips to lengths 90 of wire B, 50 of wire A, and 50 for wire B. Her readings are shown in the table. Calculate and record in table 2.1 the resistance of each length of wire. So they even give you the equation for resistance. It's voltage divided by current, so we're doing 2.8 divided by 0.32, and we get 8.75 ohms for the first resistor. And then for the next one, we've got 2.6 divided by 0.45 gets us 5.7 recurring, but we're going to round that so that it's got the same number of decimal places. Is going to be 5.78. We've got 2.7 divided by 0.54 gives us 5, but again we could measure it to the nearest 0.1 ohm, so we need to show that in our table. And then finally 2.3 divided by 0.72 gives us 3.19. Okay, so now I've done this bit. Don't miss that it says complete the headings in the table. So we'll go up here, volts for voltage, amps for current, ohms for resistance. An easy 1 mark. Then it says calculate a value P using your results for R when it's wire A at 90 centimetres, so that's 8.75, divided by R for 90 of wire B, so that's this one, so that's 5.78. And when we do that, we get a value of 1.51. Okay, it's a ratio, so it's unitless. Calculate a value Q, this time A over B, but for the 50 centimetres. So we've got 5 for A and 3.19 for B. So we've got 5 over 3.19. And that gets us 1.57. Okay. Oh, I just realised I'm not even showing that on the screen, but it should be fairly obvious to you. That gets you a mark. Okay. Then it says, a student suggests that the values of P and Q should be equal. Suggest whether your results support this suggestion. Justify your answer by reference to values from your results. So let's look back at P and Q. P was 1.51, Q was 1.57. So I'm just going to put this up here so that we can refer to it easily. Okay, so if I were to round these to 1 decimal place, I would have 1.5 and I would have 1.6. That's only a difference of, can't do maths today, goodness me, of 0.1. Okay, 0.1 out of 1.5 is less than 10%. Okay, so that suggests that actually, given that it was an experiment and there might have been errors, they're very close together, so they probably are equal. So we're going to say yes, it does support the suggestion. Okay, so the values were only 0.06 apart, which is less than 10% of the value. Suggesting this was just due to experimental error. Okay, so what we're saying is, well, our numbers are not identical, but they're so close to each other, the difference between them is basically negligible in comparison to the actual value. Okay, then in D it says suggest why students all doing this experiment, now I'm going to highlight this word because it's important, carefully with the same apparatus may not obtain the same results. I'm actually going to highlight the same apparatus as well because lots of you talked about the power supply being different or not reading the scale carefully enough, and that completely contradicts the question. We're assuming that everyone's done it carefully and everyone's been given exactly the same things to use, so we can't give those as reasons why we might get different results. So we could have said the crocodile clip was difficult to connect at exactly the right point. So if we go back to the diagram, go back 2 pages, we've got this length of wire. This will be on a meter ruler. The crocodile clip is a couple of millimeters across. We may not get it perfectly where we need it to be, where we read it. So it might be that our reading we take from different points on the crocodile clip each time. So that's something that we could talk about. Okay, we could say it is difficult to connect the crocodile clips to exactly the correct length. Okay, so that's something that even if you're being careful, it's very difficult to do, and it's going to change the results slightly. Okay, number 3. So we've got a student investigating an image produced by a lens. So the triangular object is shown full size in 3.2. Some of you measured this one, which is not figure 3.2. It says measure and record the height of the triangular object in 3.2. So we literally take our ruler, and not in inches, in centimetres, we're going to measure that height. Now hopefully you can see that's 1.4 centimetres. Okay, that's all we had to do, 1 mark. The student sets the distance u between the triangular object and the lens to 20 centimetres. He moves the screen until a sharp image of the triangular object is seen. The student measures and records in Table 3 the height of the image on the screen. Briefly describe a technique to obtain an image on the screen that is as sharp as possible so it's clear to see. Okay, so I don't know if you remember when I got the candle out and we were looking at forming an image on the wall, I moved the lens backwards and forwards until I saw the candle. But this time we're going to fix the distance between the lens and the object. So instead what we're going to do is move the screen. We couldn't do that in the classroom because you can't move the wall, but obviously if it's just a screen you can move that bit instead. So we're going to slowly move the screen backwards and forwards. Until you see a sharp image. Okay. Next part of the question says the student repeats the process and you're given some data, and it says, okay, for distance u is 20, can you calculate and record in a table the value of 1 over hi? So we're just going to literally do 1 divided by 5.6. And when we do that, you'll see on the calculator it's not a very nice number. Okay, we're not going to quote to that many decimal places. We're going to say, okay, well, it's going to be 0.18 because I'm going to take this 8 and I'm going to round up. And that means that I'm being consistent with the rest of the column, which is important. Then it asks you to plot a graph of u against 1 over h. So we're going to take these numbers, I'm going to take these numbers. Okay, and it tells you which axis to put where. So you get 1 mark for labelling your axes. So literally taking this and pulling it down here and saying, well, this is u in centimetres, and this one down here is 1 over hi measured in 1 over centimetre for our unit. That gets you a mark, and some people did miss this. The next bit is that we have to have appropriate scales and checking that they occupy at least half the grid. So let's look at u first. We have to fit 20 to 40. They're nice round numbers. So I'm going to switch to my pencil so I don't make a mistake. If I put 20 here, if I go 30, 40, I'm only using half of the grid. So this time I'm going to go 20, 25, 30, 35, 40. I know now that my points are going to span the whole grid. And then 1 over hi has to go from the smallest of 0.18 to 0.83. So let's have a little look and see what we've got. If we start with 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, that does allow me to cover at least 2/3 of the grid, so I'm going to choose that. Okay, so I'm going to pause while I plot this so you don't get bored. Give me a second. Okay, so I've plotted them. You get a mark for each plot being put in the right place, correct to the nearest half a square. Okay, so you've basically got to get it within half a square on x and y. They need to be neat crosses, not splodges, or you'll lose a mark. And you then get a mark for a thin line of best fit. So don't forget that you've got a point down here. So you wiggle it around until you can see a nice line of best fit. A tip I would give you is if you move your ruler so that it is at 90 degrees, you can see the points a bit clearer, and make sure you can line it up as best as possible. So at the moment that looks like a pretty good line of best fit. I sketch that on like so. I've got these 3 basically on the line and one slightly below and one slightly above. So that's my line of best fit. Then it says determine the gradient of the graph. Show clearly on the graph how you did this. So we have to draw our triangle. So we choose two new points, okay, that are as far apart as possible, and that are really easy to measure. So you can see, maybe you can't see, let me choose a different colour. Here and here are where I'm going to choose to mark mine out. I'm then going to connect those with a triangle, like so. And I then measure the lengths of the sides of the triangle. So I'm going to pause while I do that so you're not too bored. Okay, so I've put my triangle on. I can see that this occurs at 0.24 and this one is occurring at 0.88. I can see that the bottom of my triangle starts from 20, let's have a look, 21.5, and it ends at 41. Okay, so this length is 41 minus 21.5, and this length, or width really, is 0.88 minus 0.24. Okay, so in order to find the gradient, I do my change in y over my change in x. So I'm going to do 41 minus 21.5 divided by 0.88 minus 0.24. Okay, that's just for mine. Your line of best fit is going to be slightly different because you won't have judged it identically to mine, which is absolutely fine. So long as it matches your points, you will get the marks, so long as it is in range. And I get a gradient value of 30.46875, but I'm just going to call that 30.5 because I can't really say I'm more accurate than that. And then it says calculate the focal length of the lens, use your value of HO from part A. So we'll go back to A. And we had 1.4 centimetres. So this I'm going to write as 1.4 centimetres, and my gradient is numerically equal to the value that I just got, and I said that was 30.5. So therefore my focal length for my calculation is going to be 30.5 divided by 1.4. And that gets me a focal length of 21.7, and that's going to be in centimetres. Okay, so yours will be a slightly different focal length, that's absolutely fine. There will be a range in the exam that you're allowed, so please don't worry about that. Suggest one difficulty that can be experienced when measuring the height of the image. Suggest an improvement to overcome this difficulty. So think about what the image looks like. Actually, let's go back to that. Okay, this is what we're measuring, but if you think about where it is in the diagram, there's going to be light travelling through. Okay, and we see our image on our screen over here, which is also light, right? So light comes through the lens and we find an image on the screen because there's light. But as soon as we place a ruler here, it's actually going to block the light a little bit, which makes it very difficult to measure. So what we're going to say is that the ruler gets in the way of the light. Okay, that's a real difficulty. So it's difficult to see the top and the bottom. So what we could do is place graph paper on the screen so that the image is projected onto the graph paper, and we could mark the top and the bottom. Okay, we could then measure later. So if you think about what that would look like on your screen, if this is your screen, you've got an image being projected purely because of light. If we've already stuck a piece of graph paper to the wall, we can come along, we can put a little pen mark here and a pen mark here, and then we can measure that later. We will then be able to get a more accurate value. Last but not least, we've got the planning question. So let's have a look. We've got a student investigating the strength of an electromagnet. It's made from a coil of insulated wire. It's wrapped around an iron rod. And when we put a current through the coil, the iron rod becomes magnetised. It can then attract magnetic materials. Plan an experiment to investigate how a factor affects the number of steel paper clips the electromagnet can support. You're given an electromagnet, a power supply, and a selection of paper clips. And it tells you that you should include the things that you'll measure, the additional apparatus, state what you'll keep constant, explain how to do the experiment, talk about how you'll get reliable results, draw a table with column headings, and explain how to use those readings that you would take to reach a conclusion. So I think rather than writing a plan, what I'm going to do instead is show you how you could get each of the 7 marks. Okay, so we've got the basic setup is going to be a power supply connected to the electromagnet. An ammeter would be used to measure the current. You may well want to use a variable resistor, but if you didn't add one of those, that's absolutely fine. For the first marking point, you had to correctly identify something that you would change. So you also have to say how you would measure that. You may well have chosen to change the number of coils, so the number of turns you have on your electromagnet. Well, that's easy to measure, you just count them. You may have kept the electromagnet the same and changed the current flowing through the power supply and see how that affects how many paper clips the electromagnet can pick up. And if you stated that, you needed to say you would measure it using an ammeter. Finally, you could have changed the voltage through the electromagnet or across the electromagnet, and that would have been measured using a voltmeter. You don't need all 3 of these, you just need one because you're only going to change one thing. For the second mark point, you would have to state a control variable, so one of the following. What would you have to keep the same? Well, if you were changing the number of your coils, you would have to keep current and voltage the same. If you changed the current, you'd need to keep the number of coils and the voltage the same. And if you change the voltage, surprise, surprise, you keep the number of coils and the current constant. Okay. And then finally, you might also have said, we need the paper clips to all have the same mass. That's important as well, otherwise it's not fair to see how many it picks up. The third mark comes from writing a method. So instructions, I would always use bullet points, I would always number them. It's easy then to repeat steps. So we say set up the circuit as shown in the diagram that I drew up here, with the voltage of the power supply fixed. With the variable resistor on its lowest setting, switch the circuit on and measure the current, and then the number of paper clips the electromagnet picks up. In step 3, I say repeat step 2 3 times and find an average, okay, of the current and the number of paper clips picked up. Now, I should point out, I've referenced using the variable resistor to change the current, but you can just get away with saying change the current. They don't need you to specify how. Then I've said record the values in the table shown below, and then finally repeat steps 2 and 3 for different resistor settings so that you've tested 6 different currents. You could have just said repeat steps 2 and 3 for different current values. Find an average number of paper clips for each current value. You get the 4th marking point, so a mark, for saying that you will repeat this and test different values of your independent variable. You get 1 mark for your table having correct headings with units. So really the only thing you needed in yours was your current measured in amps and your number of paper clips picked up, but you may well have got slightly different variations based on your independent variable. I controlled my current by changing my resistor, so I also recorded that. I then, for my conclusion, said, well, I'll take the results from my table and I'll plot them on a graph. Now I don't have to draw the graph because I don't have any results, but I do have to tell the examiner what I would put on each axis. So I would record the current and how I changed it, and how many paper clips were picked up, so that I can look at if the current increases, if more or less paper clips get picked up. So that's how I draw my conclusion. And then the 7th mark, the last mark on the paper, is for saying any of these points. You don't need all of them, you just need one of them. Referencing that you need at least 5 pieces of data. That's important so that you can plot a good graph. If you've only got if you've got less than 5 points, you're not going to have a very good graph. You're not going to know what your line of best fit looks like. If you talked about repeating measurements and finding an average, you got a mark. If you referenced more than one control variable, you could have had that 7th mark. If you discussed making sure that the paper clips were placed down in the same point each time, that would have got you a mark. And if you discussed how you could have improved the experiment by repeating it and trying a new variable, that would also have got you a mark. So you get 7 marks in total for your plan. It was done very well, so really well done. I hope this video has helped.